Dear respected colleagues, greetings from Valencia, Spain. And it is my pleasure to introduce you today for a series of webinars dealing with the simulation of conditions when irrigating crops in risk of salinization. The first model that will be presented will be the hydrous one-dimensional that you will be guided by Dr. Mason Rasey, the vice chair of this network, you know already. And I will I will give some remarks in general about the models and the approaches for the situation of crop irrigation with brackish water or saline water or with soil that is already affected. So my idea is to give you a short idea in general of the models. The session of today will be the first of three devoted to the hydrous one-dimensional, and this will be in detail explained by the presenter, Dr. Mason Rasey. Today is, I think, an outlook on the model. The second day will be running several examples. And the third day will be devoted for the presentations of the attendants that they have run their own examples on modeling. And we will watch about their progresses and we will discuss about their approaches. So allow me to share my presentation. I think that now is on the screen. And this will be an introduction to the series of models. And first speaking about what is modeling and why we make modeling. And what are mathematical models? Are abstract descriptions of a concrete system, but in the way of mathematical concepts and language for making predictions and providing insight about the real world. And the process of developing mathematical models, it is called modeling and results in computer codes. Computer simulation that we will use today and next days is the use of a computer program to reproduce the dynamic response of one system by modifying the magnitude of some variables that define the real system. It is important. So we excite the system and we observe what is the response. We construct mathematical models because it is often costly, impossible, or demanding too much time to conduct experiments to study a real-world problem. And so mathematical models are ways to describe the behavior of a system and as well for predicting outcomes from perturbation of the system. I will make general considerations about the models. The mathematical representation of natural phenomena is really a difficult task. Models that are built up are simplifications of reality, hardly trying to approach it. Reality is very complex, and we many times focus on main aspects. Some models address only particular aspects of environment or just main processes that happens in the system that we want to model. The code development is based, of course, on existing scientific and technical knowledge. So it is important the basic research, and after that, the codes can be built up on the knowledge that is the background. But modeling complex situations that maybe you expect to be able to, after following the completing the webinar, it needs a lot of elaboration. So the more complex, the most elaboration needed. A general model anyway, can link several complex submodels. And it is a particular aspect that needs about reflection and how to deal with this link and passing the information from one model to another one. In the way for computing the codes approach in deterministic way, it means that only one entry gives one output, or stochastic way that you take a distribution for the entries and you get distribution, statistical distribution for the answers. Models are subject to various uncertainties derived from the way reality is represented. So if we represent it well, the model will be more accurate. But many times we do not get that. The code could be very simplified, and the uncertainty could come from the input data that we do not collect in an accurate way, and as well from the accumulation and the propagation of errors. And that's a very important point. Let's describe the idea of the models that can be empirical models. That means that the mechanism based in which the way something happens, it is not well known. And so such models can be empirical. And they can be qualitative models, are many times used for example, in geology, in descriptive geology, or quantitative. If you have a lot of data, the model is quantitative, and you can have empirical models that relate an entry with an output, and the correlation is high, but the mechanism is not well known. So there are empirical models in such a way. And there are as well the mechanistic models that you can describe with accurate equations what is happening. And the best approach is when you have mechanistic models and quantitative models. But this will be demanding a lot of data and accurate data and good equations to describe the system. But when you will see that when using a model, we take information from several scales and several models that could be not equal. I mean, for example, the most clear example is that you will use for making a forecast climatic data. And this climatic data are of global or region at least projections, and they have an uncertainty. And this uncertainty is propagated to the model that could be very accurate in the equation that describes the movement of water upwards, downwards, or laterally, or the cation exchange capacity. So we should take into account that when using a model, there could be several submodels, and these submodels are not equal in quality. And so we should think that error can happen because of that. And so it is strange that you get a very, very accurate response when you make long predictions in time for how will be the system. For example, with this climate change projections, if you make this for several years, you can see that even meteorological scientists, they give you several options, and depending of the other variables, even social, if the society moves to more complex and more industrial or less, and well, several variables. And so there are several projections of climate. And for the propagation of the error, when you make long projections for the future, as a watch that has some parts that do not match perfectly. So it means that the watch will not give exact time. Maybe it is just delayed 2 seconds every day. But when you make a prediction for 100 years or 10 years, so you must think that this error is accumulating. And so it is not accurate nowadays. Could be the error could be acceptable for 1 week in the case of the watch that I'm describing, but not for longer periods. And because so many pieces in the models, so many sub-models many times are integrated, and all of this have some not perfect match with each other, so errors with long scope in the predictions should be contrasted. It is very important to build up a conceptual model when it is a mental model. In the environmental applications, conceptual models are used to express relationships, explore and test ideas, check inference and causality, identify knowledge and data gaps, and synchronize mental models and build consensus, and to highlight key or dominant processes. And these conceptual models capture our current understanding about the structure and the workings of a system. I mean, you must consider which problem will be afforded. And as for example, this is a map of Spain. It is a geological map, and it is marked roughly where the areas that have more problems of salinity. You can see that there are inland areas and there are as well coastal areas. So this is an example of a coastal area, the Delta Ebro, that is well known because it is famous in the aspect of productivity, but as well because of a regression of a delta comparable to the Mekong or Mississippi and other deltas. And in this case, the model, when you try to approach what is happening with salinity, these points, the numbers, these points are sampling profiles, and the number, it is the average electrical conductivity. You can see it is very high. But this, how to model what happens here. This, the crops are rice, and they are managed in flooding condition all the 130 days. But in coastal area, they have as well marine intrusion due to the close to the coast, and as well by the existing of paleocanals and other aspects. So the conceptual model for this study case should take these conditions, and this as well, it is another important and distinctive condition is the reducing conditions around the root zone of the rice. And the conceptual model will take other variables. In this other case, that is an example of center of Spain, and as you can see, the satellite imagery, the salinity comes from irrigation with brackish water and inappropriate quality. And you see in white the fields that were salinized by irrigation, by drip irrigation, by pivot irrigation, and only the red color indicates chlorophyll activity. So in this case, we should not take into account the marine intrusion. It is, in this sense, it is an easier problem. So there is no permanent water flooding the field. So the conceptual model should be built up taking into account the variables that affect our system. So there is no general rule for affording the problem. You must think first about which variables affect the site that you are studying. And then as well select the appropriate code, or even in sometimes several codes. One that can deal with the marine intrusion, another for the crop growth, and you must link this several models. What is useful for the models? Should consider that salinity change a long time, and we are interested in to know how this change along the time. And we can make measurements, but they refer to a specific moment, and it is not possible to obtain measurements of the future. So it is good if with the tool of the model, we can make some forecast of what will be the conditions in the future. And measurement consume time and resources, so we should wait, and we should have money enough, and they should match the conceptual model that are the basis for the computer models, and the modeling allows us for the anticipation of processes, and then we can change conditions and check what will happen if this happens, in this condition change in the sense or in another sense. For sure, modeling is much more complex than simple measurement, but in compensation, it is much more powerful. And these models can be very complex. You can see the scheme of two models. One is monodimensional, the other is two dimensions that take into account a lot of variables and the aspects of vegetation, of the movement of water, of the condition of the soils, and so on. And in salt-affected soils, there are many aspects that can be difficult to be modeled. First is reactive transport. So there are models that only move the water and solutions along the profile, but reactive, it means that the salts and the solutes of the solution react with the clays and other minerals in the soil. So what happens should be modeled. We should consider that in many cases we are in an environment that is high in the ionic strength. So many models do not consider that, this high ionic strength, and then the predictions fail. Because you have dilute water entering the profile, for example, rainwater, and as well this water of irrigation that can be high in salinity. You can have a flow that has different densities, and this makes difficult the modeling of the movement. As well can happen change in permeability due to crusting, to the concentration of salts, the dispersion of clays due to the pH raise if it happens when the irrigation water is alkaline. And as well, if you have organic matter, this can increase permeability and enhance as well ion exchange. But models, if you are dealing with crops, they should cope with the reduced water uptake by plants due to the osmotic stress and matrix potential. So the normal growth of the crop it's not possible in such a restricted environment. And as well, other aspects, carbon dioxide production and transport and heat transport, and the chemistry of the system should take into account the chemical speciation, the cation and anions exchange, and kinetic precipitation dissolution of minerals, and in many cases as well, redox processes. What can we do with the models? Forecast of the evolution of the modeled systems. And with that, we can approach a better management and a better irrigation. That is the objective of this webinar. Determining as well leaching requirements and deciding if the crop that we are cultivating is adapted to the conditions that the field has. And as well, with models, we can make scenarios analysis, changing the conditions. For example, what if I irrigate more? Or what if I irrigate with this now with sweet water and later with brackish water and alternate? Or what if the climate will change in more drier conditions? So we can enter these different scenarios. We call that scenarios in the models, and observe what is the result of the prediction. And this helps for environmental impact analysis. It is useful for decision makers as a basis, and for defining environmental policy and agricultural policy as well. And steps. First, we need a clear formulation of the scientific questions to be answered. So to make an hypothesis, I'm referring to the mental conceptual model, and now we should make a clear scientific question. And it is important as well, conceptualization of the study case as a simplified model. So models ask for info in different ways. And we should then describe the reality, the soil, for example, in the way that model needs. And for example, you can describe as horizons, but the model will ask you, for example, in layers. And then you must choose the code that is more appropriate to be used. And if several codes are necessary, for example, codes for describing the behavior of the plant, another for what is happening in the soil, decide how you will transfer the results from one code to another one, and if you can make this interactive. You must study the parameter sensitivity. There are parameters that are asked by the program that must be determined in a very accurate way, but others are not so influencing, and you can make a coarser approach to the determination of such parameters. And you must get the data required for the starting the simulation and for the initial moment for the model. And then obtaining real data, it is important. If you can do that for after running the model, you can make, for example, a sampling several weeks later for checking if the prediction of the model are matching what is reality. And if not, so changing the tune of the model. So this model calibration is with the parameter estimation. So it is the starts. The sensitivity of prediction is one of the steps. And then we start with scenarios simulation in the way that we can make different changes in the input variables, and then you will have different responses of the model, and we call that scenarios. And then we can interpret what is the consequences of the scenario simulated. We should verify or make some checking of the accuracy of simulations and identify the model if it is useful or not, and what are the limits of the model. This is enough for the field. And as well, try to limit the uncertainty associated with the model by means of value range in the predictions. For example, regarding the soil conceptualization for a model, you can see there is a profile, and this model, for example, only takes account what happens into the soil. And then an upper and lower limit is defined. But for computing needs, you must slice this profile in the different elements. And in these elements, you can locate nodes that the computation will be provided. And then in this case, the model will compute upwards and downwards mass and energy fluxes. So if you have several horizons, you can divide every of these horizons in different layers, and then the model will run softly. If you do not make enough slicing, maybe the models that are using algebraic approach to the differential equations will stop because they cannot deal with abrupt changes. And in the model that we'll be explained today, there are 2 and 3 dimensions possible, but this model for today, the example is unidimensional, so only taking into account what happens in the vertical direction. And the models could take, you have these lines that define the profile, and they take as inputs, so they should be given the rain, the irrigation, the chemicals that are applied, and as well the evapotranspiration that happens. And the model can deal with water flow, solute transport, chemical uptake by plants, if it is linked to plant model, and the leaching, so the output of the water by leaching this with dissolved ions, and the loss of water as well by evaporation, and dealing with chemical, microbial and mineralogical interactions. And what models need? The models need entry data, and these entry data are of different quality. So you need soil properties. You must have a clear idea of the soil that you have, and you have measured several properties, only the properties that the model needs. So you will be surprised that, for example, you can make measurements that are very numerous, but the model do not use them. So, for example, mineralogy. These soil properties should be physical, so that the horizons, hydraulic properties that are difficult to determine, but exist pedotransfer functions that from the texture can approach hydraulic conditions, chemical aspects of what salts and the ion exchange, field geometry of the area, and the initial status, how it is the day that you will start the simulation. For the climate, you usually take projected rainfall and evapotranspiration expected. And as well, you need crop characteristics, how the crop will evaluate the phenology, the water need at any time, as well the fertilization need, and if you are using biocides as well. And then for the irrigation, the modality of irrigation, drip, furrow, sprinkler, or whatever, the water quality, the volume that you apply, and the number of irrigation events. With that entry, for the models make computing of the processes and interactions that happen into the soil, taking into account the energy and mass transport in a reactive way. And with that, you can get an output that is the mass and energy fluxes through the nodes for the simulation period. And you can as well get isochron profiles of equipotential surfaces for hydraulic potential and chemical concentrations that I will show in the next slide. And with this output, you can contrast the scenario conditions that you got with desired conditions for the crop and the yield that is expected, the risk of degradation of soil structure, or if you are promoting the build-up of soil salinity into the soil, and then decide it is acceptable or not. If it is not acceptable, you change entry data related to management, crop, or the schedule of irrigation or water quality to be used. And if it is acceptable, then you can get an optimization of the irrigation design, and as well, if needed, for the drainage fraction. These are such curves as output that you can get from the models. First one it is telling you the inputs, hydraulic conditions, inputs and outputs of the system for 4 depths, and the other are isochrons at different depths. The vertical axis is depth, and the horizontal axis is in one case is the potential, water potential, and then electrical conductivity and solid absorption ratio. And so you can see that with that, you can make a forecast of what will be the conditions at different depths, and then decide if the conditions match your needs, and if not, change the condition. This could be made just with a good set of data for the start, and with some step of checking if the model is running properly, and then you can make 1 year, 2 years, 3 years predictions. And you, of course, models can allow you to make 100 years predictions, but I told you before, remember the analogy with the watch, that it is mismatching. Well, the models that you can find can be as complex as this. This is a church organ of the Cathedral of Granada. And you can see that this impressive instrument, the biggest instrument in the world, the church organ. And at right, you can see how many keyboards and even for feet, and how many registers you have that. And this is, with that, it is very difficult to play such a complex partiture that needed to use feet and hands and change arrangements in the. Well, the model that you will use has many of this. It is an analogy, and so what to do? I cannot understand what should I take here. Okay, instead of that, it could be complex, but you can approach this in a simple way and then try to run easy examples with limited conditions. And then when you are able to run the model with in a simplified problem, then later you can make more and more complex. So go step by step until you get a skilled player of the model. So that's all from my side. Thank you very much for your attention. And now it is my pleasure to give the floor to the Dr. Mesam Rasei that will follow with the session of today, and we'll start with the hydros 1D dimension. Thank you. So Dr. Mesam Rasei, the floor is yours.
Yeah. Thank you so much, Professor Batul Salas, and I would like to say most welcome to all the participants, and also thanks to the steering committee of INSAS who made this kind of webinar series. So today I want to talk about the 1D model as a tool which we can use for irrigation and water management in salt-affected area, as well as managing fertigations and solute transport. So I borrowed this figure from my PhD, and then I want to talk about something before going to the specific matters and issues. So, you know, we should define, or we should find the current situation of our real world and define the problem, the questions, what we want to do and what we want to get from the approach that we want run. So, if we know what we want to do, we go to what we have, for example, the data, or how we can get the data regarding from one dimension, one profile to the whole field, or maybe in the region or national scale. So we can select the model based on this, based on the question, or maybe examine the models and select one of them. So do some or playing with a model to find out which parameter is sensitive, which parameter we should take into account and consider more specifically, and put all the knowledge together, and then try to find a solution. This is an example, you know, in the green one, the farmer in the border of Belgium and Netherlands used the uniform irrigation potato fields. So we went to the field, we did several experiments and used the 1D model, hydros, and try to find out which scenario after the calibration of the model, which scenario is the best. And we find out this part in the yellow map. This part in blue should be irrigated, and the rest should not. So within this, the farmer got like 50,000 euro per year benefits. So then we should ask ourselves what we are observing. As you see, the system, as our my colleague explained in the previous talk, then we have different kind of infiltration and complexity. So we have the forcing data like precipitation and evapotranspiration. We have some monitoring data, and we can go to the field, collect some data, dig a profile, measure the groundwater depth, or using the more sophisticated sensors, or in the traditional way. And also we can do the direct in situ or in the lab measurements, or indirect, like using the proxy data or PD transfer functions. So the question is, why modeling? You know, in the right side, I put 3 profiles from a field, and the groundwater level fluctuated between 150 centimeter to 300 centimeter within the field. So we have different kind of soil profile, which make it very complicated to decide which profile should take into account for management. So we say, okay, this is the heterogeneity of the system, and we should take into account. So because of that, because of the complexity of the system, the calculations, and then using the analytical equations will be very difficult. And recently, different kind of models try to solve these problems in time, and they give us and predict and simulate the real world situation, and we can understand or simplify the complexity of the system. And later on, as our colleague told us, we doing some scenario analysis, doing some calibration validation, and try to find a solution for the problem. So the question is, some people, some scientists probably believe that the model are wrong, or they don't want to go to the modeling approaches. But some believe that some of them are very useful and they can help us. Then the most important question is that what type of the model must be used? And another thing is, large data set is good or a good model? We will answer this question later. Here, I want to just briefly say the procedure of the modeling approach. What we should do? We should do the conceptualization, which means we have to define the upper, deeper, and bottom boundary conditions, like free drainage, constant head, variable head in the bottom, and upper part. Defining the root zone, soil layers, and everything and every evidence and professional flow pathways within the profile and in the field. So, and another thing is the model parameterization. In this case, we have to find out what kind of parameter is most important, and we should take into account and consider it. And if it's changed a different set of parameters, I mean like hydraulic parameters or hydraulic conductivity, can change the result of the model. So we have to define the good data set and try to predict the true parameter and the true like water content, the output of the model. And then we have to examine the different parameter sets. Another aspect in modeling approach is sensitivity and uncertainty analysis. Once we have the data, probably we have error in the data, we have to check them, then the uncertainty of the data should be solved or become less. And and then we put in and we have to find out the source of uncertainty in the model. Later on, trying to find out the output of model which sensitive to the parameter. In this case, I would say, for example, if we change the hydraulic parameters like 1%, how much the output will be changed. So based on that, we can say, okay, it's too much sensitive, and we have to optimize that parameter. So once we find out the situation and problems within the model, we use the observed data with the sensor or classical observation put into the model, trying to adjust the model with model fitting, some other adjustable parameter by experience and by hand, and try to find out the good or perfect or proper set of parameter, and later on we can get the result which the simulated result like have a less mismatch between the observed. So once we have it, we can do the scenario analysis to the management, and then do, for example, irrigation strategies. So after that, I want to briefly define the reactive transport models, which is computer model integrating chemical species and reaction with the transport of fluid or water phases in porous medium. So it takes distribution of, considering the distribution of solutes in space and also in time. And we can define it in equilibrium model, partial equilibrium model, and kinetic model. And some model have all of them, and some are have one of them, and we can couple them to have a better results. And in this graph, we can I would say, if we want to the model, we can go from the like tiny things and very short time to the long time, and in the space, like in the earth. So every the scale define itself the selecting the kind of the model, and here we are in the first part, in the left side, like in the profile or in the field scale. So reactive model take into account the soil system, which is considering the atmosphere, like soil moisture, which influencing soil moisture, like rainfall, temperature, gas exchange, and also plants like the rooting depth, then the density of the root, nutrient cycling, and uptakes, and also the groundwater fluctuation, and also the composition of the groundwater. However, here I just give some example of the models like hydrological tools and crop growth model, which can combine or like integrate together, get some result from each other to solve the problem that we define. Here I put provided the sources which you can use for select or like read information about different kind of models, from crop models to hydrological models, and from a very short or a small scale to the large scale. So that's was from the like a general talk about the modeling, and now I want to go to the hydros, introducing it, and later on we have a example that we use. We go together for this series for this webinar, and next week we go together, which means you install the software on your PC, and we can go step by step. And in the third session, if you have some data or some question, you can provide or contacted me. We have enough time, like 2 weeks after next week. And then in the third one, we can in interactive way we can solve the problem. So hydros 1D, 2D, 3D is a famous and very sophisticated which dedicated to the simulation of water flow, solute transport, heat transport, and we have thousands of users around the world that they are using this software, and we have more than 1,000 like application which published. So because this is very user friendly and very easy to use, however, it's somehow complicated. So as a brief history and development, I would say it started from 90 decade, and then after that the team from the US lab, Shimonek et al. Tried to develop it, and then now that currently we have the version 5, which is 1D, 2D, 3D all together. But however, we can use version 4, which is developed in 2017 and 17, and we can use it for our cases. So the application goes to the agriculture using some the precipitation or input water, irrigation, runoff, evaporation, transpiration, root water uptake, and all the matters that related to the real world situation we can consider into the model. It can use for solute transport, fertigation, pesticide transport, and pathogen and nanoparticles as well. So in most cases we have to use define the upper boundary condition, lower boundary condition, and all the things in between. Once we have the groundwater level, and if sometimes scientists try to couple it with mud flow, because the model will be more robust. So they collect the data from the mud flow, try to simulate the soil water content and solutes and other things. So it can be applied in industrial pollution, municipal pollution, landfills, contaminations, and other things regarding to the industry, like wastewater from dams and treatment systems. And another thing is in environmental, we can use it in ecological app, carbon storage, or nutrient transport in the environment, and affect also the climate change, and investigating the long-term procedure, what will happen in using this kind of model. So here I provided the link, PC progress. You can go to this and then register. Firstly, try to find out the free software, download them. There are several examples and some recent publications in different disciplines that the author tried to put in the website. So In this slide, I would suggest to read these two like publications from the developer of the Hydrus. Once in 2016, then they tried to review the recent development and application of Hydrus computer, and later on in 2024, they tried to again renew it and try to define some developments and application of Hydrus. There are very, very useful papers, and I would suggest and encourage the participant to read them. And they are available also in the website previous, in the PC Progress freely, and you can download. So the most important things in the Hydrus is that the triggered irrigation is implemented into the model, and I used it in the field. And this I said, what does it mean? Is that we said, okay, if the pressure head goes lower than the value like minus 100, then we say to the model, okay, suggest the irrigation. And we can define how much irrigation, the rate, and the duration of the rate based on the irrigation system. So once we calibrate the model, everything is ready, then we can use this kind of triggered irrigation implementation, and then the model itself try to find out based on the water potential, give us the suggestion for the irrigation. So another thing that the graphs of major ion like EC and SAR, sodium aspect ratio, is implemented into the model, and we can see the graphs. So in this slides, I want to go to the model because it's very difficult to run the model in my side and share the screen. I put the screen shots I put in the presentation, and we can go step by step to see what is the model inside and how we can use it. So if you install the model on your computer and you run it, you have this window, and in left part you have the pre-processing, and the left part is post-processing. If you click to the main process, you will have the main process window, the smaller window in the middle, and you can select what do you want to simulate, like water flow, vapor flow, snow hydrology, or solute transport, heat transport, root water uptake, and carbon dioxide transport. So the model is several modules implemented into the model, into the tool. Which said or called as a standard modules, like inverse solution, like INSAS or major ion chemistry, which take into account the aeration, transport of major ion like calcium, potassium, sodium. And this is very sophisticated, very, very, very useful in our cases if we want to go to the salt affected soil. And HP1, which coupled with Frexy and allowing the considered transport and some geochemical reaction between many different ions. And normally, INSAS can help us, and if we use this major ion chemistry, of course, it is depend on the data set that we have. Sometimes we don't have lots of data or detailed data, then we have to use a standard solute transport. So in INSAS, as you can see in the table, different species of the ion is considered, and then try to sort into the model. So we have different non-standard modules that can be coupled or can be implemented into the model, and then we can use it. But I don't want to go to them because we have the time is running out, and then we have a lot of things to say. So the equations, it's Richard's equation, and it's try to solve the water flow in variably saturated conditions, and also convection dispersion equation for solute transport, and also heat movement, which take into account the time, the soil moisture, the hydraulic conductivity curves or functions, and hydraulic dispersion. So the main as a main process, if we go to this, it's already uses the Richard equations in different saturated or unsaturated conditions. And if we use the main process in the pre-processing left side of the model, and select water flow in the middle window, and say next, then we can find out various or different kind of hydraulic models which are implemented into the model, like Van Genochten and Muallim, modified Van Genochten, Brook and Corney, and Kazugi or Ragnormal model. And then we can select one of them and try to find out which model is perfect to our case, and then we use it. And for the information, mostly in most publication, Van Genochten and Muallim was used. So we have also the dual permeability model or dual porosity. If we have the conditions like this, we can select in the middle of the middle window. And we have also hysteresis, which is included into the model, and we can select if we have it. If we have the data, we can use in hysteresis in rotation curve, or no hysteresis in the simple way. So again, if we go to the main process and check the root water uptake, so what we have is the sink term of the accounting for water uptake and plant growth, actually root growth. And it uses like the we can use the model for root water uptake, and also the solute stress model. And we can define the critical stress indexes for water uptake, and the passive root solute uptake C root into the model. And here we can say, okay, we have the passive solute root uptake or active solute uptake. It's based on the data set that we have or information that we have. Also, we can use the heat transport, define some temperature if we measure it in the groundwater or in the soil, and you use it in the file in the model. So it was about the water flow and some more information about that. And here we have solute transport, and we have three options: standard solute transport or major ion chemistry. If we again go to the main process and check the solute transport and standard solute transport, and say okay or next, and we will have the different kind of information that we have to select or we can select. And if we have linear or non-linear reactions between the solid and liquid phase, we can select the options that provided into the model. And if we have equilibrium model or non-equilibrium solute transport mode, we can also say to the model, we can define the units and the different things, like different number of solutes and other information. But it is to be noted that we have to know what we want to do. If we don't know, it's very difficult to run the model. So again, we have solid transport or transport parameter we can define into the model, like bulk density, the dispersion of the solute, and diffusion in water and diffusion in gas, and coefficient of the first order and second order as a reaction parameter. So it considers the transport parameter and reaction parameter of each solute. And we can say, okay, this is the zero order production or first order degradation by selecting or checking the data in the reaction parameter window. And so if we go to the solute transport, like we have boundary conditions, we can define the kind of the root water uptake as I mentioned already, and using the passive or active solute uptake. If we use the major ion chemistry, again, going to the main processes, check the major ion chemistry that I mentioned in the red cycle here. So what we have the different, we need the composition of our soil layers, and also the water, the applied water or rainfall composition to put into the model. So we can select the different kind of schemes. So for the moment, I don't want to go to the detail about the schemes, and we just leave it right now. Next time, probably I talk about that. So in the transport parameter, in the case of the unsaturated module, we can put the solution composition here in milliequivalent per liter, and adsorption concentration of the soil, and also precipitated concentration, which is not used in the standard solute transport. However, we are here. We have the cation exchange capacity, calcite, and dispersion of the solute, and bulk density of the soil, and this is defining here the reaction parameter of the model. And in this window shows the boundary conditions. If, for example, if we have the fertigation, we can say, okay, this is a kind of concentration from upper boundary condition, which is going into the soil. Or if you have only rainfall or maybe water for leaching or irrigation, we say, okay, this is the fluxes. Or the zero concentration in the bottom, or up to find out the solution, the solute transport within the profile. And we can use the initial condition as in liquid phase or in total concentration, which is considered all the species in the system. However, another thing it's implemented into the hydrous is the P2 transfer function based on the data set in US, and based on the texture, they predicted the Van Noten parameter like theta R, or residual water content, saturated water content, alpha, and N is the shape of water retention curve of air entering value, and Ksat is the saturated hydraulic conductivity. And it is implemented into the model once you check the main process, and then you go to the soil hydraulic parameters in the middle window up. You can use neural network prediction and select a model, like if you have only the texture or the percent of the texture, like sand, silt, clay, or other information. You can select one option and put the data in the as an input and get push the predict button. You can get the output and accept it. So you will have the predicted water flow parameter in your model. So that's the general thing about the model, and the overview of interface of the model. So sorry, I was so fast, and I hope you followed you followed me. So here we want to put in or solve the example. And I wish you follow me, and I wish you had the piece the software on your PC and try to run the model with me based on the information that I provide. And maybe later, I suggest you to run this model, play with the data set, even the synthetic data, because next week we will go further into the model, so you can actually you will be familiar with the model. So we want to simulate water flow and solute transport into a 4-layer soil profile. We have a profile. Let's say that it is homogeneous in the field. So the geometry or the depth of the profile is 100 centimeter with 4 layers. And upper boundary condition is atmospheric boundary condition with surface layer, which means we have like evapotranspiration, precipitation, rainfall, or irrigation. And maybe we have ponded water on the surface. And in the bottom boundary condition, we have free drainage, which means we don't have groundwater level like within 2-3 meters. So we consider it free drainage. Once you open the model, say, okay, then it gives you the window will open and ask you to name you name the project. I would suggest to put NIM NIM 2.5 as an example that we have here. You can name it as you want. So the situation is that we have like a field and we provided provided like 8,500 cubic meter of water for each hectare of the wheat crop for the irrigation and also as a leaching. And they suggested that use the 20 centimeter water as a pre-irrigation for leaching purposes, like 30 of that simulation from the first of the simulation. And we have 5 irrigation events, the equal amount of water divided in 5 times, 5 events. And it's suggested the day of the simulation period, and whole of the period is 1 year, like 366 days. So we open the model. So go to the main process and select in left side, you can see we select water flow, solute transport, and major ion chemistry or INSAS, because I will show you next slide that we have enough data for that, and root water uptake, which is also considered solute uptake. In the right side, we define the geometry information that we say, okay, the length unit is in centimeter. We have 4 soil materials, and the depth of the soil profile is 100 centimeter. So we put next on the geometry information window, and we will have this kind of information about the sorry, like initial time, initial condition. Let me go to the this slide. Yeah, here for time information, initial time we put 0. For final time we put 366 day. And for print time, we can use, okay, how many times it printed as a check of the data, like every week, every month. We can use it 550 in right hand photo, the print information. So in every window, we check next. Just put next to see the information, and put some the information of the example, and to see what will happen and what would be the result of the model. And if you select, okay, this is the print time, if you use like 12, it give you the default print time in day. So the iteration criteria, the model suggested to use the values here. Don't change it because it needs some experience. And if you have some different problems in the model calibration, you later on you can go to the iteration criteria, change them to find out the most the better solution for the target, for the like variables. So if you put next in the left side, do you hear me? Oh,
Yes, all fine. Go on.
okay, sorry. So then in the right hand we have a window which asks us what kind of the hydraulic model we have to select. ونگ نقطه معلم تو بزرگی do we have a dual porosity or not, or do we want to consider hysteresis or not? We select based on the real world situation. For the moment, we use ونگ نقطه معلم, no hysteresis, and go to the next one. We push the next button. So in the next button, we have water flow parameters. And as you see in the table on top of the slide, that it's provided already the silt, clay, sand percentage of each layer, the depth of the layer, the EC and pH and SAR of the soil layers, and also Van Genochten parameters. So they already provided the Van Genochten parameter, and we can use it into the model. Otherwise, if we don't have it, we can use like Rosetta. Just if you don't have all the information here is 0 in the left side, you will use a neural network prediction. If you have textural class, just use it as a loam, as a silt, as a like sandy clay loam. Or if you have the percentage of the texture and like water content or field capacity data or bulk density, you can use it here as an input, and check the predict button. You will have the data which predicted from the data set of based on the pedo transfer functions, and you can accept it. Once you accept it, the data will come to the material. For example, one, if you click in one material, first layer. If you go for the second layer, again, you can click on the window, the cell of the second or third layers, and again do the using the Rosetta, which implemented into the model to find out or predict the hydraulic parameter. So once you once we have the data set of the water flow parameter or hydraulic parameter, we push the next button. So in the next window, we have to define the boundary conditions. As you have seen in the example, they already said, okay, we have the atmospheric boundary conditions with surface layer for upper boundary, and as a lower boundary, we have free drainage. You can also find out different kind of boundary conditions here. You can use the help button, which it explains or uses the user manual of the model, explain what are they, and in such condition you can use this kind of boundary conditions. As an initial condition, just check the water content, and as a potential evapotranspiration and leaf area index. If we have it, we check this cell. If we don't have it, so uncheck it. And the maximum head of water at soil surface, we suggest that use like 20 centimeter because we have 20 centimeter to apply it as a pre-irrigation. So once we check and put all the information here in the window in the left side and push the next, we will have this solute transport window in the right side. So we don't go to the schemes here, just for the moment use the default schemes. The mass unit you can define here, the stability criterion also don't check it, use the toxicity factor. Here, I put the composition like 6. Why? Because we have 4 layers in the profile and 2 composition of solution. One is rainfall and another one is the irrigation. So we have a rainfall, irrigation, and 4 layers. Therefore, I put 6 as a number of solution concentration combination here. So as a absorb concentration combination, we have 1 soil, just put it 1. If we have more information about different layers, then we change it to based on the layers and data set, and also for as a precipitation. Normally 1 is okay. So we put once we select everything here based on the profile, based on the information that we have or observation that we have, then put next. In our case, we have 4 layers profile. So we also have the composition of layer of the saturated paste solution of soils for different layers in milli equivalent per liter, and also the composition of irrigation water and rain. So we will put all the information into the model. How, if we have the solute composition, we start from layer by layer. The model itself understands that first one is the first layer, second one is the second layer or second material, third, fourth, regarding to the material that we define. And or you can put the number 5 or 6 as number 5 and number 6 is the solution, the fluid, which is considered to be applied into the soil. So for example, here number 6 is related to the rain, the composition of the rain, and number 5 is the composition of the irrigation water.
Excuse me.
Yes.
Dear Mason.
Yes.
Well, consider the time remaining and the possibility of questions, because
okay, yeah, okay.
Thank you.
You're almost welcome. Okay. So we put some transport reaction here, the bulk density and the dispersion. Normally we take the 1/10 of the soil profile depth as a dispersion. If we have the cation exchange capacity, we put here. If not, leave it as it is, as 0. So as a upper boundary condition for the solute, we use concentration flux because every event of irrigation or rainfall has the flux of concentration, and lower boundary condition we use zero concentration. And as an initial condition, we check the liquid phase because the data comes from the saturated paste solution. So for root water uptake in the right hand, we use the FEDES model, and as we consider here as a passive root solute uptake, and we use 6, which means if we the model will like in passive way collect or uptake the solute in that value. And also we put it is implemented the model, just do the next bottom in each window once you run the model to remind you. And here you can select from the database base the crop, and it gives you some information, which means the water potential in that crop will be in the stress in water or like threshold of the salts or osmotic coefficient. That they are already in the database, and you can choose the crop. And however, you can change the values as you have the data set yourself. So that's all from the information from the parameter and adjustable parameter into the model. So here we have to define the time variable boundary condition, which is provided by the like sensor or meteorological station which installed nearby in the field, or like observation of leaf area index. I put the figure of leaf area index for wheat in the optimum situation, and you can like use this value into the model as an example and put the information you see here. The most important thing and should be noted that the precipitation in the second column, and also the irrigation amount like here in 20.93, which included the irrigation or as a pre-irrigation and also rainfall. And here as a C-top, as you remember, for the rainfall, we put in the row 6, and for irrigation composition number 5. And here we can specify the precipitation, the input water. The coding is like 6 for rainfall and 5 for irrigation or water application. And we like use this in the time specified time that in the example they said. So when we push the next and we agree to the model says, okay, do you want to do the profile application? We say, okay, just check the data set that we input into the model. So another thing that we have to say or briefly explain is that soil profile or graphical editor. Here we can define the condition of different layer, depth of the layer. Here, for example, in the left side, you can check the material distribution, and just by right click on to the discretization that my colleague explained. Just define the materials and number of materials in order of the materials in the profile, and also root distribution, and it's based on the observation in the field. You can use it, just click on the icon and try to find with the edit condition button. So we can insert the like observation point if we have sensor, or if we want to evaluate based on the depth, we can put the observation point, insert the observation point with different depth, and here is like 1 centimeter, 13 centimeter, 25, and 50 centimeter. As an initial condition, we already in the window previously said took the water content, and here we use the uniform water content at the beginning of the simulation, like 0.2. Just take the push the edit condition, and from top to bottom say okay, this value. So once we define the materials and root distribution, so we want to run the model, say okay, run this bottom here like a finger, or we have a window that say okay, do you want to run? We say okay. With this window or with finger, we run the model. Once we run the model, in the left side, we have post-processing information. If we go to the observation point, we can see the pressure head by the time, and you can see we have like 6 events, 1 for pre-irrigation and 5 for irrigation during this growing season. As a water potential and also water content, you can see we have enough water and huge water during the growing season. If we go to the next like boundary fluxes, we can see the soil water storage. In the post-processing, you can see, you can check all the options, and you can see the information here. And you can see the water storage every time of irrigation, the peaks, it goes up and down, which means water is was used by the plant, and again we have or evaporated, and again we have the water content. Here, this the basic info in the basic information option. We have also the water content throughout the profile. We can see. Sometimes the model, you have the old version of the model, and they don't give you the like EC and SAR in graphical mode. And once you save the model in the directory, you can go to the directory. You can see all the information in the folder. And if you open the observation node chemistry, you will have this like the information, the data for regarding to each node. We have 4 nodes, like 1, 13, 25, and 50 centimeter. We can take those data and then make a graph outside of the hydros. And you can see here as an interpretation, in the beginning, the initial condition, the EC was like 15 in 50 centimeter, 0 to 50 centimeter of soil, and the sodium aspect ratio was like 20. After like 6 events of water as a pre-irrigation and irrigation, the electrical conductivity or salinity of soil become less during the season. It become like 5, which it's okay. But during the summer or after the harvesting, the EC goes up. And also for SAR, also we have this kind of manner and trend. And you can see evapotranspiration during the summer can accumulate the solute upper part of the soil. That's all from my side in this session, and I hope you install the software, try to play around with the model, and probably Dr. Konyushkova will provide you the presentation and the data set, and you can use the data set that I explained here. And next time we can go further regarding to the model. Thank you so much, and thank you to all the participants, Soil Water Research Institute in Iran, and also the Steering Committee of INSAS. Thank you so much.
Thank you very much, Dr. Meisan Reisei. And now, please, Maria Kuniuskova, Dr. Maria Kuniuskova, could you make the questions that were done through the question and answers window, please?
So thank you, Jorge. Thank you, Mason. So there are quite many questions regarding the technical aspects of using the Hydrus model. And so I have this sound. Sorry. So I propose that we have a 15 minutes Q&A session.
Yeah.
And if we don't manage to address all the questions which were raised in the Q&A box, then we can address them in our forthcoming sessions, because we will have 2 more, and I think that we can address all of them later. So I would like our participants to stay with us for more 15 minutes, and then we finish. Okay for you, Nissan, Jorge?
Yes, it's okay.
Yes, please, go ahead.
Okay, so the first question was regarding what are the differences between the different Hydrus models, 1D, 2D, and 3D?
Yeah. You know, the 1D model consider the 1D column and simulate the water flow, solute transport in 1D or one-dimensional. 2D and 3D considered in lateral flow or in 2D or 3D in the real world, let's say, a situation which should define the a cubic or of the profile into 2D or 3D and ask the model to give the result in 2D or 3D view. So, and it also, of course, more complicated and more robust result you can get from 2D and 3D. But the most important thing is that there are commercial 2D and 3D, and 1D is like free. So that's why we explain 1D.
Thank you, Mason. And can you stop sharing?
Yes, sure.
So we will share in case you don't need the slides. So second question, what is the best model for prediction soil salinity in the field under irrigation with brackish water?
I would suggest Hydrus. Actually, it's very sophisticated and developed very well and updating every regularly. So I would suggest this one. Of course, different kind of models are existing, and it's based on the experience. You can select one of them, couple or integrate with crop growth model and run it, and get the results.
Okay, thank you. Then the following question, how we can increase water use efficiency by using this model and at the same time reducing the salt accumulation and soil profile?
So as you remember, you can, once you calibrate your model, etc., or even uncalibrated, just play around, you should consider the real world situation. If you have enough water, so based on the concentration of the solute and the triggered irrigation and the solute stress, just put the threshold of each and say to the model, okay, suggest me when I have to water the crop. So based on that, the model gives you some data of this irrigation. So yeah, if you, for example, to have a strategy of deficient irrigation or enough irrigation or complete irrigation, you can say, okay, I have enough water, and then use it. This is one way, and another way is that from one of my work, we run the model into the field like 50,000 columns using the data set from the field, run 1D model, try to make a map of the water content, and we have seen that in different locations, we have drought stress, water stress, and the rest we don't have. So based on that, okay, we can, in the first slide I explained, we go for the location for irrigation. This is another thing. It's based on the situation that you have for defining the problem.
So can Hydros 1 be used to map soil salinity at field scale or local scale? I would also reformulate this question, adding that what parameters do we need if we want to map soil salinity at the field scale using Hydros?
Yes. Actually, the Hydros doesn't give any map, but we have different approaches to get kind of map from Hydros. As I said, if you run the model as a quasi 3D, which means you defined in the field in like 1,000 columns, the information you need is the hydraulic parameter, concentration of solute, the layers, the depth of the layer. If it homogeneous would be fine. Otherwise, you have to have the depth of the layers in different locations. Put all the different applications, or you can run the model in batch, or you can use Python or R. And the Python will or the software collected observation or provided data, put into the model, run the model, and later on, based on the result of the different columns, can give you the map. I would suggest to read the citation, the publication that I provided in the presentation.
Okay, thank you. Then there is a question about the modeling of nitrate flow. So how much data do we need to model the flow of nitrates? For instance, I have the values of nitrates I receive every week for a 2-month season. And is it enough to model nitrate flow and uptake using Hydros?
Based on this question, which means 8 points in the profile, we should check the model, run the model to see how it's like fluctuated. Would be enough, and it depends on the uncertainty of the observation as well. If you say, okay, it's very uncertain, so it's very difficult to have a like robust result, a confined result.
I will add some info. When dealing with nitrates, you are considering other aspects in the simulation. That is the denitrification processes that happens.
Yes.
So you must activate other routines in the Hydros.
Yes, indeed. Yeah.
Okay, thank you. Then what is the minimum data required to run the Hydros model? And so if we don't have access to all the parameters, to all the data, what is the minimum set?
Actually, we can run the model for 1 hour to 1,000 hours or like 1,000 days. And it's based on the like, you can play around, you know?
I suppose it's regarding the input data. So what is the minimum data set of input data?
Probably the question goes to the variable boundary condition. As a variable condition, we can use hourly basis, daily basis, like weekly basis, or yearly basis, based on the data that we have and the time scaling. If we have like the in growing season, daily would be fine, or weekly would be fine. Probably daily is the best. So
yes,
if you have a shorter time for the simulations, or if you have like a column in the laboratory, probably 2 hours, 3 hours data set, like inflow and outflow would be enough.
Some authors run several years for making forecasts, And in this sense, it is needed to provide, for example, the meteorological data that you can approach that this is regular or more or less same. But in this case, you are entering in the uncertainty because the different variables are changing and the computing is progressive. I mean, the models do a projection and then they take that as truth for making the next projection. So
yeah, true. So it's depend on the interval that you define an available data set. Sometimes you have hourly, sometimes you have yearly. Yeah.
The next question is related to the root uptake, C root. So what is the difference between passive and active root uptake, C root in Hydrus 1?
Actually, the active
and
is
how to specify these values in the Hydrus model.
As you have seen in the like a diagram or in the window, you can say, okay, how much solutes based on, for example, if you have like the EC of 10, the model can, the crop can only uptake 6 of it in different species of the ions, and the rest will remain in the profile. Sometimes, like, you can select 5 or put 0 because the crop won't uptake any solute. Based on the experience and also literature, you can use these values, and normally the literature provided some values for different crops. And for the active, if you have like some more information, you can select active because the crop spend some more energy to collect or uptake the solute. And as you can see in the window, needs some more information regarding to the crop. And if you have it, then you will have the more real situation regarding to active uptake.
Then how does Hydrus 1 handle dynamic root growth over time? Are there options to simulate the expansion of the root zone or changing root distribution patterns?
Yes, it's a nice question, actually. It's very difficult to say because sometimes once we put the density of the roots into the model, which the model doesn't consider any change in the density, even if root growth is checked, because the architect of the root will change during the growing season based on the profile, based on the penetration resistance. So the model doesn't consider that. And based on the observation, we have to select, okay, this is the root, root density. And however, it is kind of limitations of the modeling, because sometimes they don't consider any changes in the roots, like density and other architects.
This is a case in which a combination of models is recommended. A model that can deal with the crop growth, and then you pass this info to the Hydrus. And then in this way, you get a much more accurate picture of what is happening.
Indeed, that's why we couple the crop growth model with Hydrus to get the better results and robust results. Yes.
Okay, I will ask two last questions and then we finish for today. One is about, are there any available packages on R or Python for the Hydrus model?
The open source is available, and you can find it in GitHub. Yes, it is available for.
Okay, maybe you can share the links afterwards.
Of course.
With the
Yeah.
participants. And the last not the question, yeah, it can be considered as question that what are the books and tutorials which are available for free regarding the hydrous, the using of the hydrous model.
Yeah,
If you can
actually,
recommend, maybe the participant can read
yes.
before our
Yeah.
upcoming
Actually,
webinars.
hydrous model has a user manual. Once you download the model and install on your PC, and if you go to the help option of the model, you will have the PDF file of user manual, and it explains everything regarding to the every window, every parameter, and also the table of the output which I explained in the generated in the directory of the saved model. So I would the best option is the like user manual of the hydrous for the moment, and also just reading the PC progress information, give some examples, and then just run the model with their example to see what is the outcome or results of the situation. There are publications, and based on the publication, put some data, provided the hydrous project, and you can just use it and say, okay, how they interpreted and publish the data or the information based on the data set and the model.
Okay, thank you. So as I said, we have many questions that we will address in our next sessions, and I pass over to Jorge.
Thank you, Maria, for making these questions to the panel. And as you say, there will be the opportunity to answer these questions and others that will appear for the next session. And Mason, could you please explain the attendance? How will we develop the next session? That will be next week, same time as today.
Yeah. Actually, we want to. I prefer to have a interactive or in person. I mean, as a workshop, but it's impossible. However, we use this kind of situation for the practical application session too. We have again different kind of examples, and I will try to share some information or some data with you using some like data, and I will go to the model itself, not in the presentation. I share my screen, just open the model, put some data, provide some data, prepare the data, put into the model, run the model, and interpret. Probably two study cases will be explained. And I would ask the participant who has some real world data set in their research area, just try to contact me or send or try to find out how the model will work with their data. If they have any problem, just let me know. We can solve the problem for this the third section. So for the second one, next week, we will have two case studies with hydrous and running the model, putting some data in it, getting some data from the sources and putting to the model. That's in my mind. If you have any other suggestion, also it's welcome, and I will try to implement.
So thank you very much, Mason, Dr. Resay, for your very interesting and detailed presentation. And I know that this is very difficult with such a wide model with a lot of variables to be adjusted to guide the participants through the study case. But I think that you got it with the example that you presented in the screen. And it is expected that they get familiar with that and become more and more skilled for next week. and this will be a real a proof for you, because on a live demonstration by internet, it is really challenging. But I
Yes.
think I'm convinced that you will get it. So thank you very much to all participants, and Dr. Kuryeskova, Dr. Mason, Rasei, for your participation. And so we meet again next week, same time as today, for continuing this, that is not only a webinar, but it is more like a workshop, hands-on. Thank you very much for your participation, and see you soon.
Thank you.
Thank you.
Have a nice
and
evening
goodbye.
or day. Goodbye. Bye-bye.